The last time we spoke, I described electromagnetic radiation in two ways. The first, and you might call it the primary way, as a wave of electric and magnetic fields. But then I also suggested that there were experiments that were observed in the laboratory around the turn of the last century that required us to think of light instead as particles. An idea that's carrying over into this discussion is that the higher the frequency, the higher the energy. It's possible that our understanding of that will become more sophisticated as we go, but we should start getting accustomed to the idea that high frequency means high energy. The topic for today is the electromagnetic spectrum, because we can organize all of the electromagnetic radiation we encounter as a continuum of frequency, from the lowest frequencies observed in nature to the highest. I mean, a curious thing about that is that the frequency is the only distinguishing characteristic of electromagnetic radiation, and yet it behaves very differently in terms of how it intersects with our lives, both our everyday personal lives and our scientific lives. And so it seems like there are different kinds of radiation, when the distinction is really just differing frequency. So I'm going to talk about the electromagnetic spectrum a little bit, but then I'm going to shift to giving some, but not all, of the examples of common electromagnetic radiation phenomenon and their explanation in the context of the frequency and energy of the light. So I'd better make a start. The electromagnetic spectrum is organized according to the specific value of the frequency of the radiation in hertz. But instead of memorizing all of those specific numbers, which would be a very nerdy thing to do, we have broken them up into arbitrary bands. You can actually find textbooks that differ on where the cutoffs are between these different bands of electromagnetic radiation. I've organized them here from low frequency to high frequency, and it starts with radio waves. The lowest frequency radio waves in the universe come to us from outer space, and cosmologists use the information of those waves to deepen our understanding of the nature of the universe. Pretty groovy. But in our everyday lives, in society, radio waves are very low frequency, low energy waves. They carry the music and the radio signals that come from radio stations and are used for short-range radio communication. Increasing the frequency of a bit, we come to microwaves. Microwaves makes it sound like they're very small. Well, indeed they are, but in a relative sense, that's a bit vague. Microwave also makes you think microwave oven, and that's appropriate. Microwave oven cooks using waves that have a frequency just a bit higher than the radio waves that deliver you your music. Beyond the microwaves, increasing the frequency, comes the infrared, which we can use to reveal warm objects using infrared photography techniques. And then we come to that very special band that we experience in our everyday lives, a very, very narrow band of frequencies of electromagnetic radiation that happen to stimulate the rod and cone structures inside the human eye, creating the sensation of vision. Everyone knows that if you go out, particularly we're all looking forward to the summertime, and you are exposed to waves of even higher frequency, waves whose frequency is so high they become invisible, the so-called ultraviolet waves that can burn your skin. The radio that delivers the music to you doesn't burn your skin. The infrared doesn't burn you. Certainly visible light doesn't burn you. Suddenly we come to higher frequencies of ultraviolet light, and our skin is getting cooked as we enjoy ourselves in the outdoors. Heaven forbid you need an X-ray for a broken bone or to diagnose disease. X-rays pass right through your body. And I think it may have been mentioned to you at some point, there's a limit to the number of X-rays you can get. And it may have occurred to you when you were getting an x-ray that the x-ray technician left the room and went into another room and said, okay, here we go. And you might have been laying there thinking, wait, why did you leave? Am I in danger? Well, no, but x-rays can affect the biological function of your body. Gamma rays are the highest frequency that they name, and they come from nuclear reactions and also, believe it or not, I'm going to say something crazy, from the creation of the universe, the highest frequency. They are all identically the same physical phenomenon. This is the point of this slide. They're all electromagnetic waves. The only thing that's different is the frequency. So why do they behave so differently? Well, the reason is that while I describe them according to their frequency, and higher frequency means higher energy, they also have a wavelength. And the wavelength of waves describes their physical size. Now here, the electromagnetic spectrum is shown in a very common graphic. If you Google this, you will find dozens and dozens of graphics showing this very same thing. Here on the left-hand side, I have the radio waves, and they're drawn in such a way that the wavelength is long. You see, as I go from left to right, the wavelength shortens and shortens. As the wavelength gets smaller, the frequency gets higher. It might be difficult for you to sort of envision this in time because it's a static diagram, but what's happening here in time is I'm at a very low frequency, and as I go, the frequency gets higher and higher and higher. That's the way to think about this. So, since high frequency means high energy, over here on the right I have the ultraviolet, the x-rays, and the gammas, and over here on the left I have the radio waves, organized according to frequency. And here, and because that's what's here on the I guess you would say on the x-axis of the graph. Here on the radio wave, there's a frequency of about 10 to the fourth hertz. 10 to the fourth hertz. Okay, Shidley, whatever you say. No, you knew that. You knew that was true because you're interested in getting the sports scores, and you tune into what radio station? 94, right? Okay. 94 WIP in Philadelphia. The 94 is kilohertz. That's 94,000 hertz. That's 9.4 times 10 to the fourth hertz. This number makes sense to you from your everyday life. On the far side, it is 10 to the 18th, which is 1 million trillion hertz. That boggles the mind. There's no everyday reference for that to understand that. So I've written here that the wavelength of these very long radio waves is 30 kilometers. That's peak to peak on the wave is 30 kilometers long. It's enormous, larger than mountains. And then on the high frequency side, on the X-ray side, it's 0.3 picometers, which is 10 to the minus 12 meters, which is smaller than atoms. Smaller than atoms. Again, a smallness that you can't appreciate from your everyday life. Here's the thing, sort of a mantra. You can get asked a lot of questions about this in the future. If you're looking to score well in physics, you should get used to the idea that from low frequency to high frequency, we're going from long wavelength to short wavelength, that we go from low energy to high energy. If you struggle to memorize that, just engage it. You're in no danger from radio waves, and gamma rays are known to be quite dangerous. Well, you're in no danger from a rock that's traveling at 0.1 meters per second, because that's a very low kinetic energy. But a rock traveling at 300 meters per second is a bullet. And it's very dangerous because it has a high kinetic energy. The danger comes from the energy, and the spectrum is organized from low energy to high energy, low frequency to high frequency, long wavelength to short wavelength. And it's the job of the student of this particular physics to sort of memorize that mantra so that we can explain the various phenomena that we describe. So our waves, according to their wavelength, can be very big or very small. And so I want to sort of claim that the reason why waves behave differently in various contexts, despite the fact that they're the same thing, is a question of scale. The wavelength of a wave is about physical size. Long wavelength waves interact with big things. The sizes are compatible. when the sizes are compatible, that's when you get effects. Short wavelengths of radiation, that's high frequency, high energy, interact with very small things like molecules and atoms. So radio waves interact with buildings and big radio antennas that we see, particularly around our area here near the city. There are, in the Manayunk section, there are the large radio antennas that you can see from just about everywhere, cars and rooms, because radio waves have very long wavelengths. And so they interact with those things. One of those interactions is called diffraction. Despite the fact that you may not have line of sight to a radio tower, the radio waves curve around buildings and hills because they have similar sizes and allows the signal to travel all over the place. Wavelength, or microwaves, pardon me, are about centimeter size. Your cell phones use microwaves to communicate, like the highest energy radio waves. We make a transition from radio waves to microwaves, and of course, microwave ovens. The size of the cavity inside of a microwave is on the order of centimeters. Infrared is on the molecular side because those infrared goggles that allow you to see in the dark are receiving radiation from the vibration of molecules. Visible light has wavelengths on the order of cells. That's why you use an optical microscope in biology class to look with your human eyes at the cells and various structures of organelles inside of cells. If the little biological details of the critters you're looking at under a microscope, if those little parts get smaller than the wavelength of visible light, you can't see them. And biologists have to come up with a different technique in order to visualize the smallest of the biological structures. The ultraviolet turns out to be molecular and down to the level of chemical bonds. So smaller than the biological level to the actual molecular level of chemistry. X-rays, high frequency, short wavelength, they get into the atoms and the electrons on the inner shells of the atoms. That's where we see those effects happening because the atoms are on very, very small scale, very, very small wavelength compatible. And then gamma rays are so small that their size is comparable to the nucleus of atoms, and their energy is extraordinarily high. From here on out, for the rest of the conversation, I'm just going to pick out a few E&M phenomenon to focus in on. There are many, 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 but they all have the same explanation because there's only one issue. High frequency means high energy. That's the only issue that there is. And because the speed is equal to the frequency times the wavelength, when I say high frequency, I mean short wavelength. They're related to each other that way. There's only one issue, and yet we get these strange behaviors. Here are a few behaviors of interest. Radio waves. Radio signals reach you when you can't even see the tower. It's not in direct line of sight. And that's because radio waves are very large and they can bend around buildings and hills, and we use large antennas to interact with them because the size of the object has to match the wavelength. And so they behave differently than light does. For example, if I'm standing behind a building and the sun is on the other side of the building, and so is the radio transmission tower. I'm standing in the shadow of the building, and so the sunlight doesn't come to me. I'm standing in a shadow. And yet the radio waves go right around the building, and I can still receive the radio signal on my handheld radio. This is because the visible light has a wavelength that is so short that it doesn't bend around the building, whereas the radio wave has a long wavelength and does bend around the building. Radio waves don't interact strongly with atoms or molecules for that reason, and so they can just pass right through walls. If I was to tune my radio in here to a local radio station, I would very likely get a signal. And you wonder, well, they come through the cinder block? Yes, because radio waves have such a long wavelength, they don't interact with molecules, and so they pass right through them. The walls of this building are, to a certain limited extent, invisible to radio waves. You say, yeah, but the cell phone reception in here really stinks. Yeah, it's because the wavelength of the microwaves for cell phone communication is much shorter. and it interacts with the metal structure of the building, creating interference that fouls the cell phone's ability to work. Just as a little fun little aside, I don't know if you're familiar with chicken wire. We're not farmers, but chicken wire is wire fencing that has these sort of hexagonal holes in, and it's wrapped together. If you built a room out of chicken wire, if you built a chicken coop and stood inside, you would get no cell service at all, because the chicken coop wire has a size that blocks the radio signals specifically from cell phone technology. So you can actually shield against radio signals from cell phones. Microwaves, like the microwave oven. Here's a curious question. Why does my microwave oven heat the food but not the plate? No, I took it out, the plate's hot. Yeah, the plate's hot by association. If you just take a plate out of the cabinet and you put it in the microwave for the same time that you would cook your little piece of chicken, when you take the plate out, the plate's not hot at all. The reason why is that microwaves interact strongly with polar molecules like water, and all of the food that you try and cook in the microwave contains water. And so because those sizes are compatible between microwaves and water, there's an interaction. It causes the water molecules to vibrate, and they knock against each other, and eventually that average vibration of the molecules in my food is what I refer to as the food temperature. Infrared, well, I could put a thermal camera outside my house and it can see in the dark. I can't see in the dark because in the absence of visible light, my rods and cones don't get stimulated. Well, an infrared camera is designed with photoreceptors whose size is comparable to the wavelength of infrared light. That light is then detected by the camera, but you can't see that. So the electronics does a little bit of jiggery-pokery and converts those signals, which are then represented on a screen in terms of visible wavelengths. The technology effectively receives the infrared wavelengths and then shifts them to wavelengths that the human eye reacts to and then provides them to the user. Temperature, I mentioned this before at length, and just a minute ago actually, that temperature is the measure of the average internal kinetic energy, the vibrations of molecules. And a healthy human being emits about 100 watts of thermal energy. You can feel that thermal energy when you're sitting next to your honey lamb on a cold night. You can feel their heat radiating onto you. That's the invisible radiation that they produce in the infrared range. Here's a question. What's the deal with visible light, Roy G. Biv, the colors of the rainbow, the light that human beings see? Why do human beings detect such a small range of electromagnetic radiation? Well, the answer is that what we as humans call visible light is in no way special to the universe at all. There is nothing special about visible light except this. And if you think deeply about this, it's pretty groovy. Our sun does not emit light equally at all frequencies. The human eye is sensitive to the frequencies of light that are emitted by the sun at greatest intensity. Our human eyes are designed to see the light that is available. It even goes further than that. The atmosphere of the Earth interacts with the sunlight before it arrives at the surface. Our human eyes have also adapted to be sensitive to the light that is provided by the sun, even through the atmosphere of the Earth. It's pretty remarkable. There are, of course, the other creatures on this planet have a differing range of what their vision is. Insects, for example, can see all the way into the ultraviolet. And you'll discover, if you research that the ability to see in ultraviolet gives them some kind of biologically convergent advantage of survival. Why is ultraviolet light dangerous? Why am I slathering myself in sunscreen? Well, the wavelength of the ultraviolet light is so small, that is, the frequency is so high, that there's enough energy in ultraviolet light. I can think photons here would be helpful. When an ultraviolet photon comes along, there's enough energy in that photon to disrupt chemical reactions. Ultraviolet light is sort of borderline in the sense that it's the energy at which you can start to create chemical change to molecules, and it happens, biological structures. You've got skin cells, and all of the radio waves that hit them, and infrared and visible that hits your skin cells, cannot change them in any way. And then suddenly you get to the energy level of ultraviolet, and ultraviolet radiation has sufficient energy in it to destroy organelles and cell walls and other molecular structures associated with our biological existence. And so the UV is like at a transition spot. Beyond UV is when things get dangerous, but before that, all of the radiation before ultraviolet is harmless to human beings. How can X-rays do images of people? What the heck? Well, the frequency of X-ray radiation is so small that it can pass through human flesh. It doesn't interact. It's smaller than the molecular sizes. And so it passes right through human flesh and bone. But there is a bit of absorption. So bones absorb more X-rays than the meaty parts of the person do. And so when you expose a film with those X-rays, you get more X-rays on the other side of the fleshy parts and fewer where the bone has interfered and created greater absorption. And so an X-ray is just differential absorption of X-rays that generally pass through the human body because their frequency is so high, their wavelength is so small, that the human body is nearly, but not completely, invisible to the X-rays. Why are gamma rays dangerous? The gamma rays are associated with radioactive decay, and I think we're all aware that there are radioactive substances whose radiations, if you're exposed for a long period of time, result in burns and sickness and cancer. Think Chernobyl. There are radioactive materials at Chernobyl that are emitting gamma rays, and if you even stand near that reactor, even today, you can get a lethal dose of gamma radiation destroying the various tissues of your body. The cosmos at large is also a very dangerous place. In the deepest reaches of space, the evolutionary processes of the universe create gamma rays, and fortunately, the magnetic field and the atmosphere of the Earth shield us from those cosmic rays, which are ultimately deadly to the human race, but also can cause mutation of our genome, which would upset the evolutionary biology of our planet. Sometimes these gamma rays are used for medical purposes, particularly focused beams of gamma rays can be used to kill cancer cells. Gamma rays, when focused in this way and at high enough intensity, kill all human cells. The trick of radiation therapy in the treatment of cancer is to try to kill off as many cancer cells as possible and leave as many healthy cells as you can. And obviously, that sounds like a terrible way to treat what is obviously a terrible disease. And indeed it is. It's sometimes described as trying to kill the cancer before you actually ultimately end up killing the patient. And when you're exposed to radiation therapies of various types, there are limits to how much of that the medical community has agreed that you can be exposed to through the course of, say, a year, before there are real health concerns being exposed to gamma rays. Gamma rays, super dangerous because they're high frequency, and high frequency means high energy. So all of the radiation above ultraviolet is dangerous because it can react with our cells, our molecules, our atoms, and therein lies the danger. Radiation that can affect things on the molecular scale and beyond are called ionizing radiation. I want to impress upon you this. The word radiation does not mean dangerous. The light from the sun is radiation. The visible light that we see is radiation, and the radio waves that we use to communicate is radiation. The term radiation itself has kind of become stigmatized as meaning bad, but really it's the ionizing radiation, radiation at ultraviolet and beyond, that becomes chemically active and can damage our cells, our chemistry, and ultimately interfere with atomic processes in the case of gamma rays. So here's the spectrum again. I'm just repeating for this one final run through this. The same spectrum again. Here on the left I have long wavelengths and low frequency, and on the right I have short wavelengths and high frequency, and I go in increasing frequency from left to right, from the radio waves through the microwaves, infrared, visible light, which is a very narrow band here on the spectrum, compatible only with the rods and cones of human beings, the vision of human beings, ultraviolet, X-rays, and gamma rays beyond that. And I want to suggest again that it is the onus of the student here to appreciate that this goes from low frequency to high frequency, from long wavelength to short wavelength, and most importantly, that on the left-hand side of the diagram for radio waves, the photon energy is very low, and on the right-hand side in the gamma rays, the photon energy is very, very high.